There's a Mac application that runs a 26 billion parameter language model in about 2 gigabytes of memory. Not a shrunken version, not a distilled student model. The real weight's on an 8 gigabyte MacBook Air, the cheapest Mac Apple sells, with roughly 6 gigabytes left over for everything else you're doing. The model file on disk is 14.3 gigabytes. The memory footprint is 2. And I want to be precise about why that's strange. This is not compression. The model isn't smaller. It's just not all in the room at the same time. So I pulled the entire project this morning. Source, documentation, benchmark tables, the lot, and read it properly. The engineering is genuinely elegant, and I'll walk you through it. Because once you understand the trick, you'll understand something important about where local AI is heading. But the reason I'm making this video is what I found in their own benchmarks folder. The author published a comparison that most projects would have quietly left out, a measurement on the same machine, where the ordinary mainstream tool comfortably beats his own work. It's in the second row of his results table, and it completely reframes what this project is actually for. I'll show you that number and do the arithmetic on it. It changed my recommendation. Here's the plan, what it is and what it needs. Then the architecture, the split that makes 2 gigabytes possible, and the 3 optimizations that make it fast enough to use. Then why this is a Mac project specifically, which is the best explanation of Apple Silicon's advantage I've come across. Then the measured numbers, including that comparison. Then the real performance map from actual users' machines, where I found something surprising about which Macs do well. And then the honest limits, which are substantial. Standards note, everything here I pulled from the project's own repository and documentation this morning, and where I've calculated something, I'll show the working. Let's go. What it is. An Apache licensed project, written in Swift and Metal, Apple's low-level graphics interface, which tells you immediately this isn't a port of something, it is not a wrapper around the usual frameworks. It's a purpose-built runtime for one specific model, written from scratch against Apple's own hardware interfaces. The model is Google's Gemma 4 in a 26 billion parameter mixture of experts configuration with about 3.9 billion parameters active per token. Weights at 4-bit precision, with the router kept at 8-bit, a small detail that turns out to be a good decision because the router decides everything downstream. Requirements are strict and worth stating up front. Apple Silicon only, and it needs a current macOS with the latest Metal, plus the current Swift toolchain. The validated target machine is an 8 gigabyte MacBook Air. You also need about 15 gigabytes of free disk for the model. And the author is transparent about what it isn't. Text only, no images or audio, and while it ships a local server, that server has no authentication and no encryption. It's loopback only on your own machine, by design. He says so plainly in his own documentation. I notice when a project's README tells you where not to point it. The split, where 2 gigabytes comes from. Here's the core idea, and it's clean. When you install the model, it gets divided into 2 piles. Pile 1, everything that runs no matter what. The attention layers, the router, the embeddings, and one shared expert that fires for every single token regardless of what the router chooses. That comes to about 1.35 gigabytes, and it's memory mapped straight off disk and stays resident the entire time the model is loaded. Pile 2, the experts. 30 layers, 128 experts each, about 3 1/3 megabytes apiece, roughly 12.9 gigabytes. And this pile never gets loaded at all. It sits on the SSD and gets pulled in a few megabytes at a time, only when the model actually asks. Add the resident core to a working key value cache, and you land around 2 gigabytes. That's the whole headline. And notice what makes it possible. The router picks 8 experts out of 128 per token. So at any instant, the overwhelming majority of that model is doing nothing. The project's bet is simply that you shouldn't pay memory for parameters that aren't running. If you've watched our recent hardware videos, this will sound familiar. It's the same principle as the streaming techniques we covered, but implemented natively for one model on one platform, which is what lets it go so much further. The hard part, and it's a genuinely nasty problem. Here's what makes this difficult, and I think it's the most interesting engineering problem in the whole project. You cannot prefetch. Think about the sequence. A token enters a layer, attention runs. The router looks at what attention produced and then names the 8 experts it wants, which means you cannot know which weights you need until you've already done half the work of that layer. And the choice depends on this token and every token before it, so there's no reading ahead and no pattern to exploit. The decision gets made a fraction of a millisecond before the weights are needed, and that happens 30 times per token, once per layer. 30 trips to storage per token, each one unpredictable until moments before it's required. That is close to the worst possible access pattern you could design. 3 things make it survivable, and each is a nice piece of engineering. 1. The file format is the memory format. Normally, weights sit on disk in a storage layout that has to be unpacked and converted before a GPU can use them. This project stores them in exactly the layout the graphics kernel consumes, down to the 4-bit values, and the installer rearranges the data without ever re-encoding it. So there's no conversion step. Reading the file is loading the weight. That's a small idea with a large effect when you're doing it 30 times per token. 2. The disk read hides inside work that had to happen anyway. Remember that shared expert in the resident pile? The one that runs for every token, no matter what? While the processor is off fetching the routed experts from storage, the graphics processor is computing the shared expert. The weight is buried inside work. The model was always going to do. That's latency hiding, and it's why this is usable rather than theoretical. 3. A cache with a specific and clever choice. Each layer keeps 16 of its 128 experts parked in memory. If the router picks one that's already there, it's instant. If not, it comes off the SSD and evicts whichever resident expert has been used least frequently. That word matters. Most caches evict whatever was used least recently. This one counts frequency instead. And the reason is that expert routing isn't uniform. Some experts get selected constantly across all kinds of text. Others almost never come up. When usage is skewed, counting how often beats counting how recently. And the author is honest that this is a bet. The entire design assumes routing is predictable enough for a 16-slot cache to hit often. If every token wanted a random 8, you'd miss nearly every time and the whole thing would collapse. The idea underneath what active parameters actually buys you. 2 minutes on the concept, because everything above depends on it, and it's the single most useful thing to understand about modern models. Older large models were DES. Every parameter fired for every token. A 70 billion parameter model did 70 billion parameters worth of arithmetic per token. Every time, total size and running cost were the same number. And that was simple and brutal. Modern large models are sparse. The network contains many specialized subnetworks, and a small router picks a handful per token, which produces two numbers doing two completely different jobs. Total parameters govern memory. Everything has to be reachable, because you can't predict what the router will want next. Active parameters govern speed and cost. Only the chosen ones compute. Confusing those two is the most common mistake in this entire field, and it's the reason so much hardware advice is wrong. When you read 26 billion parameters, that's a memory statement. When you read about 4 billion active, that's a speed statement. Here's the intuition I keep returning to. Think of a dense model as one enormous expert who has read everything and thinks about all of it all the time. Think of a sparse model as a vast library with a very good librarian. The building is huge, but for any given question, the librarian fetches 8 books. The building's size determines the rent. The 8 books determine how long the answer takes. And the question this entire project turns on is, if the librarian only ever fetches 8 books, does the whole building have to be in the room with you? The conventional answer is yes, because you don't know which 8 until the question arrives, and going to get them is slow. This project's answer is, fetch them anyway and hide the trip inside work you were already doing. That reframe is the thing worth taking away, and it generalizes far past one application. The question was never how big is the model. It's how big is the smallest piece you can get away with holding, and how fast can you fetch the rest. Every serious attempt to run large models on small machines is an answer to that second question. Why this has to be a Mac? Now the part that explains the platform, and it's the clearest illustration of Apple Silicon's actual advantage I've come across. Picture doing this on a PC with a discrete graphics card. To get a weight in front of the GPU, you read it off the SSD into system RAM, then push it across the internal bus into the card's own dedicated video memory. 2 copies and a bus crossing. Fine if you do it once at load time, but this design does it thousands of times a second. And at that rate, 2 copies and a bus hop per fetch is fatal. Apple Silicon has a unified memory one pool. The processor and the graphics processor look at the same physical memory. There is no separate video memory to copy into, because there's no separate video memory at all. So the sequence collapses. The processor reads bytes straight off the SSD into a buffer the graphics processor is about to run against. 1 copy, no bus crossing, no transfer step, because there's nowhere to transfer to. That is why this project exists on Macs and not on PCs. Not marketing, not preference, the architecture makes an access pattern viable that would be ruinous on the other design. And it's worth noticing the shape of that argument, because it's the general case, unified memory doesn't make everything faster. It makes a specific category of thing possible, anything that needs to move data between processor and graphics processor constantly rather than once. Now the numbers, including the one most projects would have hidden. Here's their measured results table, and I want to take it in order because the third row is the story. On the validated 8GB MacBook Air, 5.1 to 6.3 tokens per second, at a footprint just under 2 GB. That's the headline machine. On a 24GB higher tier machine, 31 to 35 tokens per second, at essentially the same 2 GB footprint. And then the third row, on that same 24GB machine, running the same model with the standard mainstream Apple Silicon toolkit, 76 to 82 tokens per second, using about 9.8 GB of resident memory and around 15 GB of graphics allocation. Let me do that arithmetic out loud, because it's the most important calculation in this video. The ordinary tool is about 2.4 times faster. This project uses about 7 times less memory. The author put that row in his own results table. Nobody made him. He could have shown you his 2 numbers and let you assume he'd won. And it completely clarifies what this project is for. It is not a speed improvement on a Mac with enough memory. You should use the standard tool. It's twice as fast and far simpler. This is not a better way to run a model you could already run. It's a way to run a model you could not run at all. 15 gigabytes of graphics allocation does not fit on an 8 gigabyte machine. Not slowly. Not at all. So on the cheapest Macs, the comparison isn't 2.4 times slower versus faster. It's 6 tokens per second versus nothing. That's the honest framing. It comes from the author's own data, and it's the opposite of how this kind of project usually gets described. One more measurement I appreciated. They break down a single decode step on the 8 gigabyte machine into where the time actually goes. Roughly, half of it is the expert reads, the disk. A third is waiting in the graphics pipeline. The rest is small. Half the time is storage, which is exactly what you'd predict from the architecture. And it means the single most useful upgrade for this workload is faster storage, not more memory. More on that in a moment, because the community data confirms it in a way I did not expect. The real machine map and the surprise in it. The project collects benchmark submissions from actual users, and I read the whole table. Here's what real Macs get. An 8 gigabyte machine on a mobile class chip, about 3 to 4 tokens per second. Slow but running. A first-generation MacBook Air with 16 gigabytes, 6 to 8. A first-generation Pro-tier laptop, also 16 gigabytes, about 8 to 9.5. A second-generation Pro-tier desktop, 16 gigabytes, 15 to 18. A first-generation Max-tier laptop with 64 gigabytes, 20 to 23. A second-generation Max-tier desktop with 32 gigabytes, running from external high-speed storage 24 to 25. Now look at those last two carefully because I had to read them twice. The 64 gigabyte machine is slower than the 32 gigabyte machine, which tells you something genuinely counterintuitive and genuinely useful. Once the model only needs 2 gigabytes, having more memory stops helping. You've removed memory as the constraint, so the variables that remain are chip tier and storage speed. The 32 gigabyte machine has a newer, faster chip, and it's reading from fast external storage, and it wins despite half the RAM. There's a second confirmation in the same table. 2 machines with identical 16 gigabytes, one on a base chip and one on a Pro tier chip. The Pro tier is about 22% faster, same memory, different silicon, so the buying advice inverts. For this kind of workload, chip tier and storage speed matter more than the memory number, which is the reverse of every Mac AI recommendation you'll read. Including, in fairness, the general advice I'd give for conventional local models where memory absolutely is the ceiling. 2 different workloads, 2 opposite answers. That's not a contradiction. It's what happens when a technique removes one bottleneck and exposes the next one. The honest limits. And there are several. 1. Prompt processing is brutal on the small machines, and this is the number I'd most want you to know before you try it. On the 8 gigabyte machine, their own measurements show a short prompt takes around 8 seconds before the first token appears. A 1,000 token prompt, a page or 2 of text, takes about 37 seconds. Read that again because it's the practical reality of this on a base machine. You paste a page of text and wait more than half a minute before anything happens. Generation then flows at 5 or 6 tokens a second. That is a batch tool, not a conversation. 2. You haven't escaped the model's size, you've relocated it. 14.3 gigabytes still lives on your SSD, permanently. If you're on a 256 gigabyte MacBook Air, which many 8 gigabyte owners are, that's a serious fraction of your storage for one model. 3. The requirements are aggressive. Current macOS, current Metal, current Swift toolchain, and you build it from source with developer tools installed. This is not download and double-click. If you're not comfortable in a terminal, this is a project evening. 4. It's one model. This is a purpose-built runtime for a specific checkpoint. It is not a general tool you point at whatever you downloaded this week. That specificity is exactly why it's fast enough to work, and it means you're adopting a research project, not a platform. 5. I have not run it. I read the source, the documentation, and the benchmark tables, and did the arithmetic. Everything I've quoted is the author's measurement or a community submission, not mine. Where this points, the model that fits is not the model you think. Worth zooming out, because this project is a data point in something bigger that I don't think is being said clearly. For 2 years, the local AI story has been a widening gap. Models get bigger. The machine on your desk doesn't. Every release pushed the frontier further out of reach, and the honest advice was always the same: run something smaller. Sparsity broke that pattern, and it broke it in a way nobody designed for. Labs moved to mixture of experts architectures for their own reasons. Training efficiency, serving cost, scaling economics. None of those reasons had anything to do with your laptop. But the side effect is that the newest, largest models are often the ones with the smallest working set, and a small working set is exactly what a memory-constrained machine needs. So the counterintuitive result, a 26 billion parameter sparse model can be more reachable on a small Mac than a 14 billion parameter dense one. Not because it's smaller, it's nearly twice the size on disk, but because the fraction that has to be present at any instant is far lower. And the second half of the story is the machine. Apple sells a lot of 8 and 16 gigabyte Macs, and their owners have been told for 2 years that local AI is for people with graphics cards. That was true when the constraint was holding the whole model in memory. It is progressively less true as the constraint moves toward fetching the right pieces quickly, which is a problem unified memory happens to be unusually good at. Neither side planned this. The labs didn't design for MacBooks, and Apple didn't design for mixture of experts. The architectures converged, and a category of machine quietly became viable for something it was written off for. That's the pattern I'd hold on to more than any specific project. The frontier of what's possible moves slowly, but the frontier of what's possible on the machine you already own is moving very fast, and it's moving because of architectural cleverness rather than anyone buying new hardware. So should you install it? If you have an 8 gigabyte Mac, yes, and this is genuinely the point of the project. You get a 26 billion parameter model on a machine that officially cannot run one. Expect single-digit tokens per second, expect real weights on long prompts, and treat it as a batch tool. The achievement is real. If you have 16 to 24 gigabytes, try it for the interest, but understand that a good 12 to 14 billion model in the standard tooling will feel dramatically better day to day. The right comparison isn't this model against nothing, it's this model slowly against a smaller model, fast. If you have 32 gigabytes or more, honestly, use the standard toolkit. The author's own benchmark says it's more than twice as fast on hardware that can hold the model normally. Reach for this only if you want the 2 gigabyte footprint for a specific reason, running a model alongside something else memory hungry, for instance. And if you have fast external storage, notice that the strongest community result came from a machine reading off external high-speed storage. Given that half the decode time is disk, that's a lever most people won't think of. Step back, because there's a pattern here worth more than one application. Every serious attempt to run large models on small hardware this year has arrived at the same conclusion from a different direction. Keep the small, always needed part resident. Keep the bulk on disk. Make the path between them as short as physically possible. We've now seen that idea in a general-purpose streaming library, in agent memory systems, and here in a handwritten runtime for one model on one platform. Nobody coordinated that. It's Convergent Evolution, and it's happening because the underlying fact is the same everywhere. Modern models are mostly idle, and paying full memory price for idle parameters is a choice, not a requirement. The other thing I take from today is about how this project is documented. 103 audited experiments, including the ones that failed. A benchmark table containing the row where the mainstream alternative beats him. A README that tells you the local server has no authentication. A requirements list that starts by narrowing his own audience. That's what confidence in your work actually looks like. Publishing the number that makes your project look worse, because it makes the reader's decision better. It's the same instinct I keep pointing at from completely different corners of this field, and it is more than any benchmark, the signal I'd use to decide whether to trust a piece of software. So here's my question, and I'll pin it below. If you run this, post your chip, your memory, your storage, and your tokens per second, especially the 8 gigabyte machines and anything reading from external drives. The community table showed that storage may matter more than memory here, and that's a finding worth confirming with more data points. Add yours to their collection, as well as to this comment section. The project takes submissions. And the broader question I'm curious about, has anyone actually replaced a paid subscription with a local model on a Mac? Not tried once, actually switched for a month. That's the number that decides whether any of this matters, and nobody publishes it. Every link, the project, its benchmark tables, the community results, Apple's own framework documentation, and our hardware guide for placing your own machine is in the description. Check my arithmetic and check theirs. That's the standard here. The real explanation, sourced in plain English, with the numbers divided out loud and the trade-offs named rather than skipped. If you'd rather own your tools than rent them, subscribe. That's what we do every single day.